So I've been meaning to count this up. I'm going to count it up. Where are we at? We're here. Not counting today. Then we review for our exam Wednesday, have the exam Friday, and then let's see. We'll have 1, 2, 3 more lectures, and then a 4th class for reviewing. That's it. Holy cow, we're there, people. Yay! So again, exam Friday, and friendly reminder that your next homework will be due Wednesday night, not Sunday. Because otherwise you wouldn't be able to look at the answer key until after the test. So that one will be on chapter 27, which we've gotten mostly through on color, and the stuff today on light waves. And that we might finish, and we'll review everything Wednesday. Groovy. Any questions about that stuff? Or anything? Hey, welcome. Sorry you missed last lecture. You better watch it on YouTube. Because it's right up your alley with penumbra and umbra and all, and shadows.
I had an allergic reaction.
Oh, I'm sorry to hear that. Well, I thought about you. All right. So, light and color. I had 2 more things I wanted to show you. I thought they'd be a good review too. Let's start with this one. So we have the primary colors of light. When you add colors, what are those 3? Red, green, and blue. Right, yeah, because you can mix those in any combination or intensity and get any other color. And in terms of science and physics, that's how all colors worked out. It's what colors add together and enter our eyeball. Now we're used to pigments and like crayons and paints and inks. There's various ways to subtract light out, and thus the light that's left combines in your eye. We also learned that you can absorb certain colors because if they're on resonance based on their frequencies, but you can also scatter them, like the particles in the sky scatter shorter wavelengths. So the purple-blue side of the spectrum gets scattered, and that's why the whole sky looks blue. And the sun, then, if blue gets scattered out, you're left with what's left, red and green, which make yellowish. Well, here's another one. When we print, printers. Do you guys, anybody do a lot of color printing? What color inks do you use? Black. Cyan, magenta, and yellow. Because they're the primary colors for pigments, for subtracting. They're the secondary for light. But that's because those 3 can be combined in any way to subtract out light to get any other color. So here was a neat little example. Here's a parrot. And we used cyan, magenta, yellow, and black, which helps with intensity and edging for the shading. And you can see various colors. Now this isn't one transparency though. It's 4. There's the yellow, the cyan, the magenta, and the black. So it's kind of fun playing around with them. How about just magenta and black? Black and blue. No, black and cyan. If we add the yellow to that, there's no magenta. And it looks almost right, because there wasn't a whole lot of magenta in this picture. But let's add the magenta. Now you can kind of see a red hue to it. There's a lot of blue in that picture. Let's remove the cyan. Let's see what we got. Now you can just kind of see the yellows, oranges, and reds. So that's how they can mix those. Technology has gotten a lot fancier, but historically, whenever they'd print like newspapers or cereal boxes and the inks on them, if you look in one of the corners of the page or the tabs, you'll see little circles of the inks they use to produce all the colors on the product. And usually there's always cyan, magenta, yellow, and black. They've gained other shades now because printers they're just making other types of ink to make their lives easier, but all you would need are these 4. So you could look for those next time you're eating cereal in the morning or something. And another one of my favorite demos. I'm going to dim the lights off, and I realized, go ahead and focus on me. I'll stand back here, because I know once the lights are off, this will be difficult. This ball I'm going to turn on. It's got light sources inside, and then I'll show you. All right, what color would you say this sphere is? Yeah, we get lots of variations. Yeah, it's kind of a light pink, magenta, purple color. So we know there must be more of that in there. But watch it now. Yeah, so what this is there's 3 LEDs inside of it flashing in sync. Our eyes can't keep up. It's called persistence of vision. We can only react at a certain rate, a certain frequency. If these were blinking more slowly, you'd see that flicker and it'd be annoying. So they make it flash fast enough. That's one reason we use 60 hertz for our electrical power in the United States. Otherwise, the lights that get powered by our alternating current at 60 hertz, that means it changes direction 60 times a second. You know about frequency now. If it was slower, like 20 hertz, it'd be really annoying. So persistence of vision. Red flashes, then green, then blue. Red, green, blue, red, green, blue. But when it's really fast, they mix together and make essentially white. This one, the blue and green aren't bright enough compared to the red. So we're seeing a little more red in there. But yeah, together, when you separate it, you can move it. So the red flashes in one location, but if you can whip the ball around fast enough, by the time the red turns off and the green turns on, it's in a new position. And that's color mixing. We're adding the light together. So you can just kind of shake the thing too. Or try this. Wiggle your head. Unless it makes you sick. That's how you can tell if some light source isn't a continuous light source. If it's turning on and off quickly, you can just kind of shake your head. Or you can put it on a string and wiggle it around. Or you can give it a raspberry. One of those, you remember with your tongue? Just block the spit from the person's head in front of you. Try that out. It works better on those like red displayed alarm clocks. But same idea with persistence of vision. And this is just mixing the red and white and green. Red, white, and green, that was good. Red, green, and blue. It's good for light painting too if you want to do a long exposure with a camera. You could. All right. So there, a little review of our colors and how they can add or subtract. So what color is this? So what wavelengths are making it to your eyeball? None of them. This resonates with all the wavelengths and absorbs them. So no visible light's reflected back. If it absorbs them all, what's going to happen to it? What's that? It's absorbing them. This light energy is coming in. All these wavelengths, they have energy. It gets absorbed. Its internal energy increases, and most likely its temperature will go up. We learned that. Again, that's why black things are better absorbers. White reflects them all, so its internal energy isn't increasing as much because it's reflecting those wavelengths. Little review. Well, now we're going to do something else with light waves. We learned about refraction. And this can, especially for non-English speakers, so I apologize, refraction is how it's pronounced, refraction. But to make sure you understand what I'm talking about, I kind of emphasize it as refraction because I'm going to introduce diffraction. So it's really refraction, diffraction, but I'll try to emphasize refraction, diffraction, even though I'm mispronouncing them. This one, remember? It changes mediums. So that's, going from air to water, air into your eyeball, out of the water back into the air, through glass. And when it does that, it's delayed. The velocity of light is delayed. Again, it's an absolute speed. It doesn't change, but the time it takes to get through the material takes longer. So we say light slows down. And it changes direction. Again, if you had air and water, and you have these wave fronts coming in, don't draw that. Here's the wave fronts. These go in the water first, before this part of the wave front. They travel more slowly here. So if this is a wave front, it's like an axle on a car. This moves slower, that will move faster relative, and so it turns, it rotates, changes direction. So the stuff in the water gets bent. It's like lags behind a little bit. Like that. Before I drew it, I just thought it'd be fun to draw it a different way. We just said the ray comes in. The wave fronts are perpendicular to the direction of the ray. And instead of going straight, it gets bent, changes direction, and refracts. That's refracts. You can see when light goes through glass, it bends, it refracts. But it doesn't change colors. Your shirt's still red, yours is still green. So we're not changing the frequency here. We're not changing the frequency. Same with sound. If sound goes from warm air to cold air, it doesn't change the song we're hearing. It doesn't seem to shift up 2 octaves or something. So the frequency doesn't get changed in refraction. But the wavelength does. Can you see the wave crests are closer together here than they are there? It went down. Why? Because light got slowed down and delayed through the material. Again, this relationship. Just wanted to emphasize that. Does that make sense? Yeah.
Is this why things look bigger in the water?
Refraction is why things look bigger in the water. Yeah, when you, like these are lenses, so you can have a light ray on one surface and this happens. You can have a light ray on another part of the surface. And it can, well, yeah. Where's he at? I thought I saw him today. Where'd he go? You guys sit in different places. Anyway, somebody asked about looking at a coin underwater a couple lectures ago. If the coin were here, light would come off of it in all directions, but the one that would enter our eyeball is the one that takes this path, and it would refract into our eyeball. We'd see the light coming from this direction. So our brain would think that the coin is over here. And so, yeah, that causes that distortion. Things can look bigger or smaller depending on whether they're going from air to water or water to air. And that's refraction. We did the prism. Do you remember which colors got refracted more? We sent white light over there, and it deflected them over here. But because they have different wavelengths, they got refracted in slightly different places. Do you remember which color got refracted more? It was blue. Most for blue. Well, violet, but the blue side of the rainbow. So there's our review of refraction, because we're going to compare it now with diffraction. This doesn't change mediums. Same medium. But it goes around an edge. Around edge. So if it's in air, it'll stay in air. But if it goes past something. So let's do one. That one should work. So I use my projector here. I have a slit in there, send the light through it. So the light's going through the slit. What I wanted you to notice is that when the light goes past this edge. Some of it gets blocked, some of it goes past. And we talked about umbra and penumbra. So you can see the umbras here. It's in shadow. No light gets there. There's a penumbra because some of the light from one side can hit here, but not light from the other. So it's kind of partial shadow. And that helps for the blurriness. Diffraction is something completely different. These light waves are coming. They're trying to get past here. These get blocked. These don't. And it kind of rotates. Diffraction is another way to deflect the direction of the light rays. And it bends around the corner a little bit. That's diffraction. So both are the bending and redirecting of light, but for different reasons. One's because it changes mediums and slows down or speeds up. And the other is because it's getting blocked. And it wraps around a little bit, so they'll spread out. So what I want you to observe here is kind of the fuzziness of the edges here. Some of that is due to diffraction, the light diffracting around the edges. I'm going to switch slits. That's obviously a skinnier slit. The narrower the opening, the more it diffracts. You'll want to know that. The smaller the opening, the more it will diffract. That means it's spread out more. The angle that it's diffracted or redirected is larger. There's more diffraction, we'd say. And can you tell it's fuzzier than the first one? We're the same distance. I didn't change the focus or the lens that's projecting it, just the opening. And this is blurrier. That's because of diffraction. Let's put the other one back in for comparison. So you still get diffraction around the edges there, but it doesn't look as bad because it's not being diffracted as much. So the opening can affect the amount of diffraction. This is true with sound waves. You can be in another room and hear sound. One is from reflections. It bounces off the walls. But it also can diffract around the door frame, or a window. The edges, it can bend around corners because of the edges. Let's see if anybody realizes. Good scientists make observations. Which frequencies in music do you typically hear further away or more around a corner? Say you're 3 rooms down, and if somebody's playing their music. What frequencies do you normally pick out more conspicuously? Good. Some of you observe it's the low ones, with lower frequency. Which means what about the wavelength? Longer. That's due to diffraction. Longer wavelengths are diffracted more than shorter wavelengths for the same edge or opening. I like to think of it. If you have a small opening and a certain size wave, and you try to, it's going through there, it's not totally accurate, but it works for the analogy. It's like it's harder to get through. It's affected more, so it's diffracted more. Take a longer wave now. It's even harder to get through. This big wave through a small opening, so it'll be diffracted even more than that first one. And so longer waves, bass frequencies, diffract more than the treble notes. And let's show you that one. I have 2 lasers here. And well, the higher frequencies don't diffract as much, bend around corners. So if you're like 3 rooms over, they don't make it to you.
Oh, because they just go straight in.
Yeah, they don't redirect as easily as the longer waves can redirect due to diffraction.
Gotcha. Okay.
And there's also the energy in a long wave versus the amplitude of them. Usually bass notes have a bigger amplitude and carry more energy. So that's in there also. But yes.
So when you're in a choir or ensemble thing, and they only have 1 soprano, because their notes are freaking loud and obnoxious, is it because it's in a large room so they don't have to bend as much, and therefore the higher?
Oh, that's a great question. And I just realized I never followed up on a demo I did with that would discuss that. So let's think back. Remember when we did the range of hearing? Do you remember what the range is? We'll review. 20 hertz to 20,000 hertz for a healthy, normal, average human. So when we did that, I didn't change the amplitude. Some of you couldn't hear it really low, and some of you couldn't hear it really high. But do you remember in the middle, somewhere in there, it got really annoying? A lot of people think I turned it up, the volume. I didn't. I just passed through different frequencies. Our ears respond non-linearly. Around 3,000 to 4,000 hertz, we're more receptive to. And so they sound louder to us, for this, even though they're the same amplitude as different frequencies, other frequencies. Thus, sopranos are closer to that range, and the treble, higher overtones and whatnot of a symphony, for that matter, overshadow some of the lower bass notes sometimes. That's why you can hear one soprano over 10 basses. We're more receptive to those frequencies. However, the basses, frequencies and wavelengths would diffract around the corner better than the soprano's note would. So if you leave the room, you won't hear the soprano as well, for that reason. So let's send some light. No. Speakers. A lot of people are more audiophiles. That's why they put speakers in a box. Maybe I'll bring a demo out Wednesday if I remember for review. The speaker pushes forward and back and compresses the air, right? Well, if it goes forward, it compresses the air in front of it. Behind it, it spreads it out, right? So these are out of phase with each other. It's like a crest and a trough, a compression and a rarefaction. They're out of phase, the notes in front and back, the waves. So you do this. Well, the waves go, but they diffract around the edges of the speaker. They bend around that edge, diffraction. So the waves in the front can interfere with the waves in the back. So they superimpose, and if they're out of phase, they destructively interfere. So if you have a speaker just going like this, it's not as loud because you're diffracting the waves around, they're superimposing and destructively interfering, thus lessening the amplitude you hear. Put the speaker in a box. Now the waves that are in front, they still diffract around the box, but the waves in the back are in the box. Those two waves can't interfere, and it's actually louder. It's one reason we put speakers in a box, and we designed the box. You can design the box too so that there's a standing wave created in there that can come out in phase with the front and make it even louder. If you design the box just right, the size and shape matters. But it's destructive interference because these waves diffract and interfere. So let's send light through an opening, more fine than our light over there. So here's a laser beam, and I'm sending it through a slit. So it diffracts around both edges, and there's two edges. So it bends around one, bends around the other. And remember our waves where they came together from like speakers? Oh, we mimicked it on the overhead and my laptop. And the wave fronts came together, and in some places they constructively interfere, in some places they destructively interfere. Light is a wave. It'll do the same thing. So we're diffracting it through the edges, and the waves bend. But where they overlap, well, there's constructive interference because it's really bright. There's destructive. Do you see the dark spot? Light is coming together there, but they're out of phase, so they cancel. So in phase, out of phase, in phase, out of phase, in, out, and you get this pattern, which is a telltale pattern of a single slit diffraction. Yeah, those little things you put on the front, it's diffracting the light. Then they interfere constructively and destructively to form the pattern you're seeing. Exactly. I think I have one. You've seen those glasses, you put them on, and you think it's 3D, but you can look at Christmas lights or something and you see snowflakes and bells. Those are diffraction gratings. When light goes through it, it diffracts, the waves interfere, and form through that interference the pattern you see. Okay, I'm going to change the size of the slit. let's just pick a direction because I don't remember which is which, and we'll just look at the pattern. Okay, what happened? So some of you in the back might not be able to see it that well. There's still the pattern there. Can you see the light and dark spots? Yeah, it's like a lot of them now. So is the light spread out as much? No. So there's less diffraction. This is less diffraction. A lot of people want to think it's more because you can see more of these. It just means because they're not spread out way over here and getting dim. So we can see more of the pattern, but can you tell the angle's narrower? They're not getting spread out as far. If there's more diffraction, they spread out more. So we have less diffraction. What do you think I did to the slit? Made it bigger or smaller? We got to vote for smaller and bigger. Somebody break the tie. Bigger. And the way I remember that is if the opening's bigger, the waves can fit through it and not be affected as much. So there's less diffraction, like this. So yes, it got bigger. Let's make the opening narrower. Whoa. You can really spread it out. And you can see now there's more spreading. The angle's bigger. There's more diffraction because they're being diffracted more through that narrow opening. So two things affect diffraction. You want to note the size of the opening. If you make it smaller, they get diffracted more. But also the wavelength. What kind of light's coming through it? The size of the wave. So, for example, if we were to replace this red laser with a blue laser, which I don't have, what do you think would be different? The amount of diffraction, but which way? Step it through. This is red. How does its wavelength compare to blue? Red is longer, so we're going to get a shorter wave. There'll be less diffraction because it can get through the same opening easier. Smaller waves can fit through, so they're less affected. So if we replace this with blue light, which have shorter waves, there'd be less diffraction. And it would come back and look more like this. Whoop, like that, but being blue. So the wavelength matters and the size of the opening affect diffraction. Question?
So why can you see green laser pointers on the stars and not red ones?
Another great question. And it's the same answer as your other question. So can you think of the answer? Why do we see green lasers better?
Interpretation is not linear.
Right, our eyes aren't linear. We are more responsive to green wavelengths and frequencies more than purple.
The two things that affect diffraction are the size of the opening and the waves.
That's correct. The size of the opening and the size of the waves both affect the diffraction.
So why isn't that we're more sensitive?
Physiologically, yeah, are those sensors, the red, green, and blue cones, for the same intensity of light, green looks brighter to us, the way we're designed, made. So yeah, if you had the exact same power and amplitude, red laser and green laser, and you can do this with laser pointers, get one that's 1 milliwatt, 1 milliwatt. They should be the same brightness, same amplitude. Shine them. The green will look so much brighter for the same battery power, full battery power. And that's just because we're more responsive to the green range, just like we're more responsive to about 3,500 hertz with sound. It's also another reason why, even though the sky scatters purple light even more than it scatters blue light, we don't see it as purple. Our eyes aren't as responsive to purple as we are to blue. If we were built differently, it might look more purple to us.
So, do all stars give off all light, or are there actually some stars that only give off a specific spectrum of light?
Excellent question. Stars are not created equal, and it depends on the gases that make them up that determines the light they give off. Now, rephrase that. You guys have learned if something is just hot, if it's hot enough, its peak spectrum based on its temperature can shift into the visible range, and we see it. It glows hot like a fire. Or if you heat something up enough, like your space heater, you'll see the coil glowing orange. It's gotten hot enough to shift its peak frequency into the visible range. And so the heat from stars like that will give off all visible colors. But the gases that make it up only give off certain frequencies. They don't give a continuous range. And that's what's called spectroscopy. Spectroscopy. So we can look at a star. That one I'm going to go make a note. Well, I'll bring this demo Wednesday so you can see this. If you look at different gases that I light up, they each have their own fingerprint. But how do we tell? We send the light through diffraction gratings. So I'll give you guys glasses where the lenses are diffraction gratings. So the light will come through your glasses and it'll diffract into your eyeball. Different wavelengths diffract different amounts. You probably could have guessed because they have different wavelengths. And so you can spread light out with diffraction, just like we did with refraction. And so if a star is made up of only specific colors, we can see those specific colors. And we know exactly what gas is on that star without having to travel there. Spectroscopy, that's what astronomers do. They look at the light, they diffract it. Oh, this wavelength, that one, that pattern with those exact wavelengths, oh, that's helium. We know there's helium. Historical aside, we didn't discover helium on Earth. We discovered helium first on the sun through spectroscopy. Wow. We hadn't seen that fingerprint pattern yet. They figured it out and called it helium. Helios. That one's interesting. Yeah?
So I understand how the wavelengths affect this diffraction, but I'm kind of having a hard time picturing like the size of the opening, because if there's less surface area to bend around, then like how does, for the Umbra effect, like how does that have a different effect?
Yeah, how's the size affect it? Well, let me show this one again, and I'll more of a conceptual way, since this is a conceptual class. So the waves are getting diffracted here and here. They get bent around, but in the middle they're not as affected as much. And so there's less interference here in that sense. But you know, the wave gets diffracted around this edge. But if you got far enough away from this edge, let's exaggerate, we're way over here. We're thinking of a big wave now. It won't seem like there's much effect over here for the wave. Yeah, this huge wave comes and it hits just this edge. And sure, it gets bent. It's traveling this way and it kind of turns this way. But by the time you're over here, it's all uniform. So you don't see much of the difference. As over here, where this was going in one direction and this is going in a different direction. Same thing happens with this. So as you get the openings farther apart in here and down the road where it's passed through, you don't see as much diffraction.
And so that's why those little black spaces are caused, because they diffract, the waves cancel out each other.
Yes, the black is where it cancels out. I'm going to show that another way right after this. I guess that was what that was for. Let's do it. So, here's my little makeshift wave. You can think of these as two sound sources, or the light coming from two separate edges, the sides of the slit. Waves come off of both of them. And they're diffracted. So you got some spreading this way, some that way. At some point, these waves come together, like that. And can you see right here? They've both traveled the same distance, kind of like our sound wave experiment. Here they're constructively interfering. Again, you got waves diffracting and diffracting. But these two, we're just focusing on two. They come together at this spot, and this would be a bright spot. That's like right there, or any of those bright spots where it constructively interferes. At a different position, like say, whoops, there. At this location, they're destructively interfering. They're out of phase, so that's a dark spot. So you'd see a bright spot here, dark spot there. Keep going. You You can't tell so much because it goes off the screen, but you get the idea. They're going to be in phase again. Bright spot or loud spot. And same on the other side. Out of phase, in phase. Out of phase, anaphase. Any biology majors? Okay. So that works with all waves. They can diffract, sound or light. Let's diffract some more. I have another laser set up to go through. This one is going through 2 slits. So we have 2 edges here and 2 edges here. They're both creating that pattern we saw before, but then those patterns are superimposing and interfering as well. And so you see an additional thing. You know what? Let me turn this one on and we can compare. It's the single slit. Let's make it about the same size, there-ish. This might be a little easier, dimmer. All right. So this was the single slit. That one makes sense. That's the double slit. You can see the single slit pattern superimposed there, can't you? The center one and then side ones. But within each of those bright spots, it's subdivided again. There's more destructive interference. That's because we have 2 slits interfering with each other. And so you get even more interference, and it starts beating it up. If you keep adding slits and more slits, and then you have lots and lots and lots and lots of slits, that's called a diffraction grating, a whole bunch of slits together. And this pattern gets more defined. These little dots become very individualistic, and you can get better resolution that way and form these cool images in our glasses. But again, single slit, double slit, but it's still diffraction, superimposing of waves, and they constructively and destructively interfere. Here's some different apertures. Let's do a hair. This is somebody's hair. I don't remember anymore. All right, I got to find it. There it is. Shift, shift, shift. Okay. So as the laser beam goes past the hair, let's rotate that a little and make it tighter. Okay. So I'm moving the translation stage, and there we go. Hair still has 2 edges, right? It still diffracts when it goes around it, and we can still see the interference pattern on the screen. You can tell how thick someone's hair is by the amount of diffraction they spread out. We used to do that in the lab at Colorado State University because it was a little more fun than just measuring openings. Yeah, take your own hair and see how thick it is. People with curly hair, it changes depending on how you rotate the hair. It's elliptically shaped. So you can get it, the cross-section to change width size. And you can see it because the diffraction pattern changes. What else do I have? Here's a circle, just a hole. Okay. There it is. It's a little dimmer. But it diffracts circularly. We get these concentric rings of constructive and destructive interference. Can you guys see that way in the back? Oh, good. You can tell that you can see light and dark spots.
And what are you passing it through?
A hole, a really, really small hole. If I make the hole smaller, it'll diffract more. But then it gets dimmer because it's spreading the intensity out. If I make a bigger hole, those rings will get closer together because it's spreading out less. Let's do...
For example, in photography, if I make a pinhole and the hole is big, the quality of and the resolution of the image is...
That's right. In photography, you send light through a hole, it's going to diffract. If the hole gets too small, diffraction is more dominant, and it can cause your image to not be as sharp and as in focus because there's diffraction limits. The hole can only get so small before diffraction starts messing up the image. Good.
Yeah, but with the pinhole, if you have the tiniest is the hole, the sharper is the image.
And yes, there's 2 things going on, and I know we discussed this. The smaller the hole, the more the light gets through it is concentrated. And you're taking, getting rid of a lot of optical defects from the outer rays because they can't get through. However, there's a limit. It gets sharper and sharper and sharper as you get smaller for that reason. But at some point, diffraction is going to take over and mess that up as you get even smaller. So there's a balance of how small a hole you can get and still keep it.
And the proportion probably with the distance where the light is gonna hit.
Yeah, the distance from your screen affects that first part. And the size of the wave affects the second part, diffraction. This is a grating that it's a bunch of slits vertically and horizontally. And so it diffracts in multiple directions. And there's a lot of them, so you can see that the diffraction is getting more specific. And you can see the bright spots.
So you put there a grid.
Yeah, this is a grid, exactly. If the slits get even closer and closer and closer together, we're going to have more diffraction. These are really close together, so it's a really small opening. And look at the first one, way over here. And there's one on the other side. That's a lot of diffraction. It helps us resolve different colors better. If we had different wavelengths, they would go to different spots because they get diffracted differently. And last but not, no, this one's fun. Two more. I have no idea what this one looks like, but it makes that pattern. It's cool. So they use computers and Fourier analysis, for those of you that have heard that in math. And here's one of those types of glasses that you can wear. And the pattern that's on here causes diffraction so that when they interfere, you see the light come together as a smiley face. And it's great. Let's diffract just white light. So I put a diffraction grating on the front of the projector, and you can see now which color gets diffracted the most. Here's the white light from the center. It's going through the diffraction grating in the front and spreading out. And the different colors spread out different amounts. Who gets diffracted the most? Red, which is opposite from refraction. So in refraction, the smaller wavelengths, blue, got bent more. In diffraction, the longer waves get diffracted more because the longer waves are affected by the edge and the opening more. If I rotate the orientation of the grating, you can diffract it in different directions. Woo! And get it out of focus. Anyway. All right, let's do some more interference. Is this making sense to y'all? I think you'll like this one. Oh. Okay. So you can't see it, but I'm dipping a frame into a bubble solution, bubble mix. And suspend it. Get this out of the way. Shine some light on it. And align things. Okay. There it is. So I have a frame. It's rectangular. It's holding the bubble, a sheet of bubble. The light's coming to it, and it reflects off the surfaces of the bubble, the front and the back, because bubbles are transparent. So it reflects off the front and the back. That light comes through a lens that focuses it onto the screen so we can see it. The lens flips it upside down. It has a focal point where it brings all the rays together, about here-ish, and then they change sides as they cross over. So our image is upside down. This is the top of the bubble frame. That's the bottom. You can see the solution going down with gravity. But what's neat, my point here is, this is called thin film interference. You've seen those colors in bubbles, right? I hope. You know where those come from now, completely. So the light comes off. The light that reflects off the front surface of the bubble comes to the screen. Some light goes through the bubble. It refracts into the bubble. Some of it refracts out the backside and leaves. But some of it reflects off the backside. Still with me? Refracts through the first one, reflects off the back, comes back out the front, refracts again, and comes to the screen. So we're getting light from the front and the back. But they've traveled different distances, just like we did on the overhead with the waves. They could be in phase or out of phase, depending on the distance they traveled to the back of the bubble and back, out. You with me? So they can constructively or destructively interfere. Since different colors have different wavelengths, the thickness of the bubble, the thin film, determines which color gets subtracted out. One of those wavelengths will be destructively interfering because they'll be exactly out of phase. The others won't because they're slightly different size. So let's pick one here. What color is this? Ish. Yeah, well, this is for simplicity. Call it cyan. What two colors make up cyan? What two colors? I haven't heard it clearly yet. You'll want to know this for the exam too. Blue and green. Blue and green make cyan. So what color is being subtracted out? Red. So right here, I know the thickness of that thin film bubble is diffractively or destructively interfering red wavelengths. That extra path length of traveling to the back and coming out is causing red to be exactly out of phase right here. This is kind of magenta. That's red and blue. So green is happening there. And so you can use thin film interference like this actually to map the thickness of the film. Does that make sense? You can see that they get really close together up here. That's the bottom. That's where the fluid's settling. And it's changing thickness more at the bottom of the film where the fluid is collecting than it is at the top. Can you see how it's spreading out here? There's a bigger region here that has this relatively same thickness compared to up here where it changes a lot more. And so this is another diagnostic tool that scientists can use. They can use the wavelengths of light to determine how thick or thin things are. This interference, we can use the resolution of light waves instead of just our meter stick and be more accurate with a lot of things. So next time you see a bubble, you can think of that. Or oil on water. It's trying to refract between the two mediums. And you see those fun colors? Try to think it through. Oh, that's yellow. What two colors make up yellow? Red and green. So you'll know, oh, the blue wavelength must be destructively interfering with this interference in thin films. Okay, questions? So there's only one thing left one main thing left in this last chapter. It's polarization. And I can cover that at the beginning of Wednesday, and then we'll review. So I do encourage you to bring your questions, look over the past homeworks, and we'll go over all this one last time. Thanks.